Hello, my name's Shad Griffin. Today I'm going to be talking to you about the IBM Predictive Analytics portfolio. And I guess before we get into the actual presentation and demo, I just want to give you an idea of who this presentation is for. And I guess most of you are probably familiar with the four personas: the business analyst, the app developer, the data scientist, and the data engineer. This particular presentation and demo is pretty much catered to the data scientist crowd. And there's a couple of things that I want to mention before we get into this, is that data scientists, I think they all have in common the fact that they're trying to solve complex business problems, primarily using math, logic, and computing. But I think you also have to keep in mind that data scientists come from very, very different backgrounds. And I would say that, just my opinion, is that I think data scientists and data science has become kind of a buzzword, over the last few years, and because of that, I think it has a slightly different meaning to whoever's talking about it. In other words, I think it's very possible that you could be talking to somebody about data science that you don't know very well, and that particular person you're talking to is going to have a different understanding of what data science is than you do. And so I think you have to be very clear when you're talking about data science that you understand your audience, first of all. And I think you have to be sensitive that there are going to be people who are in the data science community, consider themselves data scientists, that may not fully understand data science in the same way that you do. And I don't think it's that data science is that uncommon. I see this a lot, like, for example, analytics. I mean, what does that really mean? It kind of depends on who you're talking to. So I think it's a pretty common thing, but it's just something to keep in mind that, even though data scientists are all trying to do the same thing, they come at that, they come at the problems that they face from very, very different perspectives. All right, any questions? All right, so I guess this slide is kind of, I don't like to present it, but I think it's important because it's hard for me to present it without showing my age. 20 years ago, I remember when I was first kind of get involved in this industry, and I guess what has become known as data science, although it wasn't data science back then, it was just called statistics. But 20 years ago, it was complicated enough, but compared to what's going on today, it was really pretty simple. I mean, you had 3 or 4 commercial, well, really 2 or 3 commercial vendors that sold software. And in the corporate space, there were others, but there were really only 2 or 3 that had any market share. I mean, it was SaaS, SPSS, and in some industries, in some verticals, MATLAB was a player. But what you've had, and then the databases were all pretty simple too. I mean, they were structured databases in most cases. A lot of times they were flat files, survey data. Did a lot with survey data back then. But the data all had pretty simple relationships. It was pretty simple. It was pretty simple, really. But what you've seen in the last 20 years, and really in the last 7 or 8 years, is you've just seen this mushrooming of technology. And right now, it's just growing at an exponential rate. And I mean, you've got all these things nowadays that didn't even exist 2 or 3 years ago. Things like Spark, and even things like Hadoop and MapReduce, and all these other different things that are really new. And I think as working in this field as a data scientist, I think it's hard. One of the hardest things that you face is the confusion, and just trying to understand what's important, what you have to learn, what's nice to know, versus what is a need to know. And it's really become a very complex environment. And it's really got to the point where I have data scientist on my title now. Although I'm still not sure exactly what that means. But, I'm a data scientist. I've accepted that. But, there are people out there who have the same title. And, you know what? If I had to step in and do their job, I couldn't. Because I have no idea what they're doing. And, these same people, and there's people on the phone today that are like that. I'm certain of it. But then there's people, there's also people that are data scientists that are 10 times smarter than me, but may not know exactly what I'm doing. So it's just a very complex environment, and that's kind of what we're dealing with. Our biggest obstacle is confusion. It's a major confusion. Confusion is a major factor when you're trying to engage in data science today. Okay, having said that, I think there are two primary problem-solving kind of techniques. And again, nobody does either one of these exclusively. I think everybody does a combination. Um, but in the extent of how these are combined really depends on the person and their background. But the first of these kind of problem-solving methods is what I would call data mining. And the idea behind data mining is that you're going to use big data and modern computing to understand relationships that are not immediately obvious. So the idea here is you approach a problem really with no preconceived ideas about the solution. You typically have, a target, something you're trying to predict, and you have predictors or independent variables that you're going to use to make that prediction. And you kind of set it all up, and you let you divide your data into a test, into a validation data set, and then you let the statistics and the math and the computing kind of do its thing and optimize the target with the predictor variables. And when you're done, you get an answer, you get a prediction based on the targets or the inputs that you put into the model. This type of thinking's been around a long time. I think it really started to gain prevalence in the 50s and 60s, and in the last 15 or 20 years, it's really mushroomed, really blown up just in terms of the computing technology that's available today, that it continues to grow and get less expensive. There's a lot of benefits to this type of approach. One is you're almost always going to get the most accurate predictions. I mean, if your problem is a prediction problem, like you're just trying to predict some outcome, you're almost always going to get the best answer using data mining. Another good thing about it is you typically get a very objective outcome. And you see these competitions. I think they're called Kaggle or Kegel, something like that, where they basically say, here's your target, here's your inputs. Whoever builds the best model wins. And that's a very objective. There's a very objective way to determine who wins. It's who has the highest prediction accuracy. So there's definitely benefits, and definitely a lot of advantages to it. The other type of approach that I see today in the market and kind of in the business environment is more of a theory-based approach. And this is full disclosure. I mean, this is where I come from. This is very prevalent in the social and physical sciences, and I'm an economist. So this is kind of how I was raised and grew up. But the idea behind a theory-based approach is that you're going to use a theory to understand your data before you even engage in computing. So you're going to try to use theory to try to understand the relationship between X and Y's. You start with a theory. You don't start with data, an input and output. You start with actual theory. And the idea behind this goes back to pre-computing, as we know it today anyway. And I'm old, but I'm not that old. But I had professors when I was in school who used to tell stories when they were in graduate school back in the 50s and 60s, and how if a professor that they were working with had a problem he was trying to solve or to publish some research or whatever, he would literally write the data on 2 pieces of graph paper, and he would give one copy of the data to one graduate student and another copy of the data to another graduate student. And they would go into different rooms, and they would literally, by hand, using matrix algebra, calculate, estimate the statistical equation, whether it was a regression model or whatever. They would do it by hand, manually, and then when they were done, they would come back to the professor and they would show the results. And if they matched, great, we're done. If they don't match, guess what? They get to go back to their rooms and do it again. So you can imagine that if this is how you're doing your computing, there's this extreme premium on the number of variables that you're going to include in a regression equation, for example. So if you include 4 variables instead of 3 variables, it's going to be a lot more manual effort. So there was a premium on theory. There was a premium on understanding that you weren't just going to willy-nilly throw data into your equation. I mean, you were going to throw our variables into your regression equation. You were going to make sure before you included it, and you asked those graduate students to go spend half the afternoon doing matrix algebra, that variable was theoretically relevant to the problem you were trying to solve. So this, like I said, this approach typically comes from the physical and social sciences. There's a lot of benefits to this approach as well. Typically, you don't lend yourself to overfitting. I mean, one of the goals of this approach is a parsimonious model. And if you've got a strong theory behind your model building, you typically, parsimony is just basically means simple. Simple is good. Fewer variables you include, the better. So you typically don't lend yourself to overfitting when you have this objective. And it's very useful when you're trying to understand the relationships between variables. For example, you're not interested in necessarily the prediction itself as much as you're interested in the relationship between your x's and your y's. A good example of this would be pricing. When you're doing a pricing exercise, you're not really interested in pricing. You're typically trying to understand the relationship between the price and the amount that's sold. And you're not really trying to estimate the amount sold as precisely as possible per se. You're really interested in what changes in price are going to result, what changes in price are going to do to quantity sold. So you're really interested in that beta coefficient, the relationship between price and quantity. And with this type of problem-solving approach is very conducive to that. Another thing is these models tend to be simpler, which makes them easier to deploy. In terms of the types of users that I typically see, in data science, from a software perspective, there's really two. And I think these are pretty self-explanatory. There's your coder and your non-coder. And like with the theorist and the data miner, I don't think anybody's exclusively one or the other. I think everybody is some combination of the two. I think that's pretty much true here. I think me personally, I guess there are some people who are exclusive coders, and some people who are non-exclusive coders. But I think a lot of people like myself do a little bit of both. I use code when it makes sense to use code, and I use a GUI type of application like a modeler when it makes sense to use a modeler. And there's a trade-off between these tools, and because I think what you get with a GUI tool is you get extreme ease of use. I'll show you a modeler in a minute. It's very simple to use. It's drag and drop, connect, and run. It's very simple. The problem with GUI tools, though, is that you lose a lot of flexibility. You don't have the flexibility to do some of the things you would have in a traditional coding tool. So there's a trade-off. Coding tools, on the other hand, are extremely hard to use. You have to learn the coding language. It can be, they can be extremely difficult. But there's a tremendous amount of power and flexibility in coding tools. So I think the best platform contains both. And that's where we're headed as an organization. So what does all this mean in terms of what IBM's trying to do? So we've got this marketplace where confusion is kind of the norm. And what we're trying to do in response to that is we're trying to come up with a platform that's going to make data science a team sport. So that's our goal. We're going to make data science a team sport. Because right now what you have is you have Joe over here doing R code, and you have Sally over there doing Python, and you have Mo over here doing SPSS modeler, and there's really not a great way for those people to communicate and collaborate. So in our new platform, DSX, what we're trying to do is we're trying to bring together all these disparate groups, this very heterogeneous group, to a platform where they can all use different tools, they can interchange the tools, and they can work together and be productive and really truly make it a team effort, because that's really hard to do now with everything being so disparate and people come to the discipline from so many different perspectives. So the new platform, you're going to have your coders, your non-coders, your coders, your non-coders, your open source, theory-based approach, data mining approach. It's going to be one platform where all these people can come together and collaborate and share. And I'm not going to spend a lot of time on it right now, but let's jump into data science experience and just kind of take a look at what the new platform looks like. And I can get there from any browser just by going to this is Firefox. I can go to datascience.ibm.com. Okay, and the idea behind DSX, it's a pretty simple idea, but I think it's very effective in solving a complex problem. Sometimes simple is good. But, DSX is built on projects. So the idea is that, anytime you have an analytical project, you would start a new project within DSX. And inside of your projects, you're going to have two primary elements. You're going to have your analytics and your data, you're going to have your assets, and you're going to have your community. And your assets can be one of two things right now. They can be some kind of notebook, but in the future, the very, very near future, you'll be able to add modeler streams as another type of asset. So you'll be able to have your coders and your non-coders working on the same project in tandem. Data assets, right now, this particular notebook I'm looking at, or this project I'm looking at right now, I have a -DB asset, but I think pretty much anything with an IP address you can connect to. Also, you can drag and drop data up here, and it will go into your Spark cluster. And you can access that as another data asset. But the big thing here is the collaboration tools, the community tools, and there's several different ways several different elements inside of DSX that facilitate community. I'm not going to go into all of them today, but I will touch on a few. This one right here, bookmarks. This is really cool. You have these things called community cards. So like if and you can add these to a project. And what this means is that these are specific things. A community card is just like it can be a data set, it can be a notebook, it can be an article, it can be something that it's a research element that you would use as you're working on an analytics project. And by bookmarking these and putting them inside the project, it's available there for everybody to see. So if I were to kind of let this project alone and come back and somebody else comes back in a year from now, they can see exactly the research elements I used to put together the project when I did. You can also establish collaborators, and you can decide who works on this project. And not only can you decide who works on this project, you can decide what level of permission they have. They can be a viewer, editor, or admin. So again, I'm not going to spend a lot of time going into all the nitty-gritty details of the tool, but I just want you to understand that what we're trying to do here is we're combining data assets with a community. And that's the vision of our product, because by doing that, you're not only you're providing a platform where people can do data science, but also share that data science and communicate with other data scientists, and this truly will make data science a team sport. We try to get people, regardless of their background, regardless of their perspective, to come to one platform where they can collaborate, share, and move their organization forward. Okay? All right, so the case study we're going to be looking at today revolves around comes from the National Highway Transportation and Safety Administration, and it's their complaint database, and it has roughly 930,000 records. Okay, so basically the way I understand that it works is, I'll call this NHTSA. NHTSA is a federal agency, and pretty much anything running down the road, they want to keep track of. If it's running up and down the road and it's related to transportation, they want to keep track of it. They don't want to keep track of you or your 9-year-old, but they want to keep track of your car, the trailer, and the car seat, anything related to transportation. So, and the idea is that they keep this database. So if you have a complaint, you can pick up the phone, I guess, or send them an email and complain, and they'll keep track of it. And they use this to, hold automakers accountable. So if they see a spike in, for example, brakes for Honda Accords, they're going to pick up the phone and call Honda and say, hey, Honda, what's up? So it's just a consumer database of complaints about auto-related things. In the first use case, we're going to explore the complaint history on a specific year. In this case, it's the 2006 model year, but it could be any of them, really. And we're going to develop a segmentation based on the make and model. So a lot of times you see segmentations based on consumer behavior. In this case, we're actually going to cluster or segment the make and models. So the Honda Acuras versus the Chevy Geos and all the different types of cars that were made in 2006. We're going to have to do a lot of great deal of data shaping. We'll look at the raw data, and then we're going to have to do a lot of data shaping before we get it in a format where we can actually do the segmentation. Okay, so in this use case, what we're going to do, just to kind of save what we're going to do before we actually do it, we're going to start off in Modeler, and we're going to generate an SQL query. We're going to take that query, and we're going to integrate it into DSX. We're going to use DSX to shape the data. Then we're going to export that data back into a -DB database, and we're going to use that shape data to build a segmentation in Modeler. And the reason that I'm kind of going back and forth is to kind of, because for me personally, like I said, I tend to use coding tools and GUI tools together, because I think they both have they both have their role in kind of the analysis process. And for me personally, generating SQL code, using Modeler to generate SQL code is kind of a no-brainer. It's a lot easier than just typing it out. I like using the GUI tools to do data shaping because you have so much control over what you're actually doing. So I'm going to go back and do all my data shaping in DSX in the Jupyter Notebook. And then I like the tool inside of Modeler to build segmentations. I mean, I think it's slick with the box whisker plots and the pie charts and all that stuff. So the idea here is that I've got DSX and I've got Modeler, and I'm going to use each. I'm going to leverage each for what it does best. And right now, the canvas isn't part of DSX, but it will be. And when that happens, I think this demo will be easier to kind of move exclusively on the DSX using the canvas instead of the actual desktop client model. All right, so are there any questions here before I jump into it? All right, so let me jump over here to SPSS Modeler, and let's take a look at our data. All right, this is the core database right here. And again, I'm hooked up to a DB database. And it's kind of what you would expect. I mean, each record has a complaint ID, and the complaint is, you just who, what, when, and where about the complaint, who they're complaining about, what they're complaining about, when the complaint occurred. This field right here, the vehicle component, is something I'm going to make use of in my segmentation. It's just kind of the element of the car that they're actually complaining about, where it happened, and then just all kinds of attributes about the vehicle and things like that, things that you would expect. And I'm going to filter out of here. We're only going to be looking at the model year 2006, so I'll put a filter right there. I've got two other tables here, and these are tables I actually created. They're not coming from the NHTSA. The first one is is what I call the manufacturer fact table. And one of the things about this table about the database is that there's things in there that aren't cars. And I really wasn't interested in anything about cars. I mean, there's motorcycles. I mean, it's literally anything related to transportation running up and down the road. So, I mean, there's motorcycles, there's trailers, there's car seats, I mean, all kinds of stuff. So I created a table. I summarized all the manufacturers, and I created another field called auto. So if it was a major auto manufacturer, your Hondas, your Nissans, your Chevys, General Motors, that sort of stuff, I populated this field with the 1, otherwise I left it 0. So I'm going to filter out everything that's not. I can use this field to filter out everything that's not an automobile. The second field I have is related to, or the second table I have is related to the complaint of the vehicle component. And I created another field called the complaint group, because when I do my segmentation, I'm really not interested in all of the variations of airbag complaints. I mean, I don't really care that there's a complaint. I don't care to distinguish between this complaint right here and this complaint. To me, they're just both airbag complaints. So I'll actually use this field right here to drive most of my segmentation. And to get kind of an idea of how many records we have in the table, about 52,000, 51,817. All right, notice the purple here. One of the really cool things about Modeler is something called SQL pushback. And the way that SQL pushback works is that when you're hooked up to a database, in this case DB, and you execute a query, or you execute a process in Modeler, it's going to figure out if what you're asking it to do can be more effectively done in Modeler or more effectively done in the database. And in this case, we're joining tables and we're filtering and just basic SQL. It's a no-brainer. I mean, you can do this a lot more efficiently than database, as opposed to pulling all these records down, applying your filter, joining them together all on your desktop. So all that information, all the data processing here wasn't done on my desktop, it was done over the cloud inside the database, and that's why you see the purple lights. And one of the benefits of that is you can actually have access to the SQL that was generated. So I'm going to copy this, paste it here. Then I do have to go in and replace all of the quotes because, and then I could use this SQL in anything. I'm going to actually use it in Data Science Experience in a minute. So anyway, so let's go ahead with that. Let's go ahead and so now that we've got our data, we've got a query that can actually pull our data. We're going to switch over to DSX and we're going to do our data shaping. All right, so I'm going to go into my projects, go into NHTSA complaint analysis, and this is the notebook I'll be using. It's called Prep Data for Segmentation. Another way I can use the community is here I can add comments. So hey, check this out. And then anybody else who comes in and uses this notebook will see whatever notes I'm making, which is kind of neat. All right, so I'm going to edit this notebook. All right, so let's go ahead and let's clear all the output out. And let's just start our notebook here. So the first thing, I'm going to connect to the database. Then I'm going to establish the database. Then I'm going to use these next two blurbs to connect this one to connect to the database. Here I'm going to define my R libraries. Is everybody familiar with R libraries? Well, if you're not familiar with R libraries, these are things. R basically is a source language. It's a base, but all the power in R really comes from these different libraries that you install separately that are developed by the open source community. This one right here, we're going to be making a lot of use of. This is called the IBM DBR. This is something that IBM actually created and made open source, and it does what we talked about just a minute ago. It does in-database analytics from inside of R. So you can actually do in-database processing. All right, so we'll connect to the database. And then we'll go in and we'll take that query that we just got out of SPSS Modeler, and we can use that to pull our data into DSX. All right, so this should look familiar. We've got the complaint group, whether or not it's an auto, which these should all be 1, the ID, the make, the model, the year, the manufacturer, the vehicle component. All right, so we have to do a lot of data shaping here before we can really do a segmentation on it. At least the segmentation that I like the best. So I'm not going to go through every step here, but the next several steps in my R notebook are all for shaping the data. So let's look at what the data. I'll run these and we'll look at what the data looks like after we get out of the shaping exercise. And in case you don't know, shaping, it means the same thing as data transformation, data engineering. There's a lot of different names for it. All right. So we have taken the data that originally looked like this up here, and we have completely transformed it. So up here we had 1 row per complaint, basically 1 row per complaint ID. Now we have transformed it so we have 1 row per year, make, and model. And then for each thing that they can complain about, we have the percentage of complaints for that particular year, make, and model that received that each component has. So for example, 36% of the complaints in 2006 for the 2006 Acura MDX were related to transmissions. 5% were related to the engine. Down here, for the 2006 BMW 325i, 36% of the complaints were related to airbags. And about 0.5% were related to stability control. Okay, so we've completely reshaped our data. And the reason I did this with the code, my personal preference, and that's the great thing about having all these things in one platform with multiple tools, is you can leverage the best each tool has to offer. I like doing this sort of thing with hands-on, with the code. It's more efficient for me. However, could I have done this in Modeler? Absolutely, I could have. All right, so now that I have this data built, or I have this data created, I'm going to write it back up into the DB database, and I'll do that right here. All right, so I wrote it back up to the DB database. And could I do my segmentation here? Can I build my segmentation here in DSX? I absolutely could. I just have to install the right libraries and go about it. But I think when you're building a segmentation, I think the tools inside Modeler are really pretty amazing. So I'm actually going to build my segmentation inside of Modeler. I did my data shaping in DSX. I'm going to do my data shaping. I'm going to do my segmentation in Modeler. All right, so let's switch back over to Modeler. And let's preview the table that I just created. And this should look familiar. We've got, for each row, we've got the year, make, and model, and the percentage of complaints for each complaint group. 36% of the complaints for the 2006 Acura MDX related to transmission. All right, in terms of segmentation, my philosophy when it comes to segmentation is just that if it's actionable and it's explainable and it's usable, it's a good one. I don't think you necessarily have to have laser beams and rocket science in a segmentation. I mean, a lot of times a simple crosstab is all you need. With deciles, or it just depends. I mean, so that's kind of how I approach it. If it's actionable, it's great. And you know what? There's no perfect segmentation. It kind of depends on what you're trying to do, and there's a lot of subjectivity involved. So I went through a lot of different segmentation methods to try to find out what worked best. I ended up on a two-step approach. I'm not saying that's right or I'm not saying that's wrong. It's just kind of what I came up with. And when you're evaluating so to build a segmentation in Modeler, I mean, it's very simple. All you have to do is define what fields you want to add and include in your segmentation, which in this case is all of those fields that I created in my data shaping that are related to the complaint group, what they were complaining about, the percentage. And once you define that, you just hit run. And then your segmentation diagnosis tools are really great. And they're in the form of your golden nugget here. So if I drill into my golden nugget, and right off the bat, I can see, I have a percentage of segments expressed, the percentage of cars that are in each segment based on shown in a pie chart. And this is really good to see this right off the bat, because obviously if you have 99% of your cars in one segment, that's probably not going to work. In this case, I have the largest one is 33%, the smallest one is 5.2%. That's not great, but I think it works for what I'm trying to do. Another thing that's real important when you're creating a segmentation is defining your segments, because the statistics behind the scenes, they don't know that. They just see the math. I mean, they don't really know what those segments mean. They're looking for clusters of data from a mathematical perspective. So it's up to the analyst or the user to go in and actually define what each segment is. And we have a really great tool for doing that inside Modeler. And you might be able to find something like, you could do this in an open source tool, but I don't think you would find near the diagnostic tools that you have in Modeler. It wouldn't be available open source. All right, so this is really great, the cluster comparison. So it tells you kind of what defines each cluster. And this is a box and whisker plot. And the center line right here is the overall median for everybody. And then the blue dot here would be the median for this particular cluster. So you can see for speed control in cluster 5, it's a little bit less than average. But if you roll down here, scroll down here, you can see the engine, the median percentage of vehicles in this cluster that had complaints about engine was substantially higher than average, than what it was overall. So this segment, cluster number 5, is really defined by cars that have a much higher complaint rate, have a lot more complaints about engines. Cluster 5 is defined by cars that have a lot more complaints about engines than other cars. Cluster 2 is defined by cars that have a lot more complaints about airbags, and then latches, locks, and linkages. Cluster 8 is defined by cars that have a much higher than average number of complaints related to speed control. So you kind of get the idea here. This tool is very great because it allows you to go in and diagnose your clusters, because the math behind the scenes doesn't really know that these cars are complaining more about speed control. It really just understands that these tend to cluster together from a mathematical or statistical point of view. All right, so we can also look at these in a pie chart with the actual labels on there. So you can see this is the count. This particular group, the biggest issue was airbags. This group, the biggest issue was child seats and brakes, transmission streams, engine, steering, speed control, steering lighting, etc. Or you can also just look at it from a list perspective. You can see these cars right here. Their biggest issue had to do with exterior lighting. These cars, their biggest issue had to do with airbags, etc., etc., etc. All right, so any questions? All right, so in the second use case, we're going to go in and let me get back over here. In the second use case, we're going to look at the historical trend between 1995 and 2014. So I don't think I mentioned a minute ago, but this database goes from 1995 through 2014. And we're going to look at the complaints that have occurred over that time period on a monthly level. And we're going to look for spikes. I mean, we're going to look for periods where the number of complaints really shot up. And we're going to determine whether a spike occurred through the context of a time series model. And once we determine when the spikes occurred, if or when the spikes occurred, then we're going to do a root cause analysis. And I'm going to do this both in Modeler and DSX, just to kind of show how you can do the same thing in both tools. And then there are some advantages to doing it. I'll show some things in really cool feature in the diagnosis that's available in R, DSX, that you can't do without some kind of R extension in Modeler. All right, so we'll go back to our data, and this is the same data we looked at before. This should look familiar. I mean, I'm hooked up basically with the same tables. Auto. This is the actual complaint database, and then this is the complaint group. The only difference is that I'm going to include everything, so I'm not going to filter out 2006. So when I join all these tables together, this table right here, the complaint database, has roughly 937,000 records, 937500. When I take out the ones that are not automobiles, I get down to about 866,000. And then there were also some that didn't have a valid complaint group, so you really didn't know what they were complaining about. You knew they complained, but you didn't really know about what. And when you take those out, you end up with 851,000. So that's what I'm actually using in what I'll aggregate in my time series model. And again, this is the data. It's at a complaint ID level. So it's one record per complaint, basically about 850,000 or so. We can't really do time series analysis on the data in this format. I mean, we have to go in and transform it, right? We have to turn it into a time series. So we'll do that right here with an aggregate node. Aggregate by file date, and then convert that to a year and month. And once we do that, we end up with this. We have the number of complaints that occurred in this month. So in January 1995, this is how many complaints we had. February 1996, this is how many we had. So this is a traditional time series, so we can actually look for spikes now. All right, so this line right here is the predicted line. The circles are your actual line. This shaded area right here is your confidence interval, so it's your 95% confidence interval. So anytime you see an actual value that's significantly different than the predicted, that means we had a substantial jump or decrease in complaints. So for example, right here, I'm not sure what happened here in 2004, but in that particular month, we had a lot more complaints than we were normally having, that we normally had according to the trend. So this is what we thought would happen. This is what actually happened. So this would be a significant spike. Also right here in 2001-ish, 2002-ish. But here in 2010, I mean, we have a lot of activity going on. We have this point right here, this spike right here, which is substantially above the what we would expect. We have this one right here, which is on the fringe of the confidence interval. And then we have this one right here, which is still pretty far away from the mean, or what we would expect, the predicted value. So the next question becomes, is we have this big spike in 2010, well, what caused it? And we can diagnose that with just a simple bar chart. So on this axis right here, we have the different complaint groups, and here we have the percentage. And then the blue bar is going to represent the percentage of events in 2010. The green is going to be the percentage of total in other years. So anytime the blue bar is greater than the green bar, what that means is that the percentage of events related to that particular component were higher in 2010 than it was in other years. So in other words, anytime the blue bar is greater than the green bar, that's probably what's driving our spike in 2010. So a substantial increase on a percentage basis for that particular component, complaints about that component in 2010. So you can see there's this one right here, vehicle speed control, transmission, and then steering, and then fuel system. So when was there a spike? There was a spike in 2010. What caused that spike in 2010? You had a change in the fuel system. You had an increase in the fuel system complaints, steering, transmission, and vehicle speed control. Any questions about that? Okay, and then just to close the loop here, you can actually do, obviously you can do the same thing in DSX, and you can develop this, you can go back and forth, kind of like I did with the segmentation, kind of switching back and forth between the tools. But let's do the trend analysis. Let's take a look at that in DSX. This might take a minute or two. So here's your trend line right here. You can see the spike right there in 2010. And then you can actually decompose this in R. And what you're really looking for, this would be your observed. I won't get into a lot of details here, but what you're really looking for when you decompose it like this to find an abnormality is the random effect. Because this should be, this is what's not explained by your time series model. And in this case, you see this huge jump right here in 2010. And then we can also go in here and evaluate that spike using the R tools. And again, I'm just showing that you can do this in both. So it's really a matter of personal preference, which one you like to use. And since they're all on the same platform, um, and you can mix and match these tools. And you can see the same thing here related to transmission, speed control, that kind of thing. So once we get these on the same platform, whether or not you're an R user or an SPSS user, you can literally collaborate and share and move your organization forward and solve problems like we were solving here. So that's generally all I have. Are there any questions at this point?